Hello, everyone. Welcome to the Toronto Machine Learning Society Annual Conference. My name is Aarti Malhotra, and I'm glad to be your moderator for today's session. It is a pleasure to introduce Senthil Nathan Sivaraj. Senthil Nathan is a principal physical design engineer at Tenstorrent. Prior to Tenstorrent, he has worked on physical design of high-performance CPU cores and interconnect fabrics at Marvell Semiconductor, Flex-Logix Inc, and AMD. May I now request Senthil Nathan to present a sneak preview of next-generation machine learning hardware. If anyone has any question, please feel free to post in the chat. We will have a Q&A session after the talk. Over to you, Senthil Nathan.
Thank you, Aarti. Welcome to my presentation. Today, I'm going to talk about our next generation machine learning hardware we have been developing here at Tenstorrent. The goal of this presentation is to give a good overview of our hardware architecture, as well as explain its scale-out capability, which is very important for modern-day training. So before we go into the presentation, I would like to give a quick intro about our company. Tenstorrent was founded in 2016. We have over 140 employees in Toronto, Austin, and Silicon Valley. As of today, we have raised $220 million US. We are backed by legendary microprocessor inventor Jim Keller and good VCs like Eclipse, Real Ventures, and Fidelity. The goals of the company is to really create a very high throughput parallel computation AI machine, which can be used for general purpose as well as for ML inference and training. Also, we want to make sure that we have a very robust, useful software stack, which can really cater to the ML needs. And also, we want to make sure that the solution really scales from edge all the way to data center. So typically, before I go into what the SOCs we have been doing, I would like to touch upon the typical AI chip design goals. Most of the AI chips these days are trying to find the right architecture for the data flow. They also want to make sure that it has the right compute capacity, it meets the performance, and for edge applications, they want to make sure that it also meets latency and low power goals. But more importantly, the most important thing, which we feel is important, is the solution should scale as per need. As the models are growing, you don't want to have a very large solution, which might work, but it's something more than what you need. So if an architecture can really scale as per the need of the ML designer, that's exactly the right chip for the AI needs. So sort of like pay for what you need. So what happened in the last 10 years has been there has been a spectrum of new architectures for deep learning, which has been evolving. It started with CPUs from Intel and AMD, and then the GPUs were the next class of compute which found the right fit for ML workloads. But then this third segment, which really is catching up now, is what's called as the deep learning DPU units. These are very custom AI hardware built for ML needs, and there are soft DPUs which are FPGA based. And there are hard DPUs, also known as TPUs. Google pioneered this. And there are a whole lot of other companies which are trying to get the right architecture for DPU. There are other areas of exploration where people want to do in-memory compute. But as of today, the DPUs are really the main drivers for AI application. So currently, if you look at the market, there are GPUs, there are custom AI silicon like Tenstorrent and a whole lot of other companies. And also there are analog photonics-based compute, which are also emerging these days, which are trying to scale, which are trying to address the model growth from a different angle. If you look at GPUs, primarily they are HBM-based. There is a high bandwidth memory. And the baseline computer architecture really evolved from graphics. It just that people stumbled upon that GPUs can take care of the machine learning workload. But if you look at the custom AI silicon approach, this is basically making sure that the architecture has the right amount of SRAM, and if required, it can go to DDR. But more than that, it's the compute architecture is really designed for AI applications. It's not just a general purpose ALU. You look at exactly how the ML workloads, what kind of compute it needs, and the floating point unit inside these architectures typically have the right architecture for custom for AI applications. And GPUs are generally expensive because of HBM, as well as because of HBM, GPUs tend to be very power hungry, while the custom AI silicon solutions are cheaper because they are more customized for exactly what is needed, and it actually uses less power because there is no HBM. On the analog side, they're still trying to figure out what's the right architecture, but the analog solutions are targeting to build the cheapest compute element, and it's mostly an emerging field. And if you look at GPUs, they really started with very high precision floating point, 32 64-bit, which was resulting in inefficiency. But if you look at typical custom AI silicon, they are really low precision, and it really results in low power and a very efficient silicon. And because it is low precision, you also need less memory on chip. So that really prevents the need for high bandwidth memory or expensive memory, using DDR. The other thing is, in terms of scaling, GPUs are trying to scale through NVLink. NVLink is NVIDIA's scaling link, while the custom AI silicon solutions are going more industry standard PCIe or Ethernet, which in our case, like Tenstorrent solution, you will see further in my slides how powerful it is for training. And the analog custom guys feel probably the model growth can be handled because they are trying to build a smaller design. But just to contrast between analog and digital based designs, like GPUs and custom AI silicon solutions are really proven silicon design methodology, while analog is just getting revived, and it has its own challenges of variability, and getting it mass produced might not be very straightforward. So, I mean, having given a quick preview of the AI solutions available in the market, now I would like to switch gears and talk about what we have been doing here at the Tenstorrent. So Jobris was our first chip. It was a test chip. And as you can see here, we had compute cores, that the T in the box is the compute cores. And we started with a single channel of LPDDR and 4 channels of PCIe Gen 4. And this was really a proof of concept chip, which was trying to enable our architecture and our software. And it was a test chip to prove it really enabled the direction of our future chip. Moving on, we developed a Grayskull in 2020. So it had more number of 10.6 cores. So each of the compute core has its own special arithmetic floating point unit, as well as its own memory. And in Grayskull, we had also 8 channels of LPDDR4 and PCIe Gen 16. We did not have Ethernet, but this was again the next generation, which was trying to scale in terms of our architecture, and it was trying to really pave the way for our future chips. So moving on, we currently have Wormhole. Wormhole is our flagship product. This was really designed for training and scale out. So what I meant by that is, like, with as you can see here, once Ethernet, we added 16 ports of 100 gigabit Ethernet. This really opens up the scale out capability of creating a mesh of cores for the programmer, and also using the right amount of hardware based on the need. And it had 120 10.6 cores, and we were also able to improve the performance inside our floating point units, and also improve the power envelopes. So Wormhole really was an evolution from Jawbridge and Grayskull. We had some key silicon improvements on PPA, power, performance, and area. We were able to improve the compute and also provide a high performance DRAM interface. And as I said earlier, like, the 100 gigabit Ethernet really opens up the scale out capability. You can start connecting these modules to create the right configuration for your needs. And this really opened up our system level focus. More from a chip level, we are now building systems which can be used as a system level approach. So some more highlights on the silicon improvements, details on that. So we improved our floating point 16 performance. Our custom arithmetic engine really had more abilities to execute complex math and SIMD instructions. Based as part of the evolution, we are also increasing the SRAM size, which is very important. You want to contain the compute inside the chip as much as possible. Anytime you go across to get data, that's when the performance hurts. And because of DDR, we have this 384 gigabytes per second total memory bandwidth, and also the 16 lanes of 100 gigabit Ethernet. And more importantly, as part of this development, we have what is called as a network on chip. So it's an interconnect fabric which connects all our cores. I will give more details on why our NOC is powerful, but this is one of the key differentiating factors. This NOC allows the traffic to move from one chip to another chip. In fact, any other configuration very seamlessly, which is very important from the software point of view. You can build a mesh of cores, but you also want to make sure that from the programmer point of view, it really appears like a mesh of cores without any overheads. So over here, you can see that Wormhole really opened up the building block for our larger system approach because of the Ethernet capability. We also have a PCI card-based system, but really Wormhole module is basically opening up the scale-out capability of our solution, where with the Ethernet, we could really move the packets in a very seamless fashion. So over here, you can see one of the configurations possible with our Wormhole module. You can see what is called, this is a Nebula solution. It's like a server solution where 32 Wormhole modules are laid out in a 2D mesh fashion, which gives a 9600 gigabit Ethernet for external connectivity. And also it has 4 gigabyte SRAM with a very good server class performance numbers. So this is another configuration. We just saw the server configuration. This is a rack configuration where 8 Nebulas are interconnected using the Ethernet to form a rack configuration. You can see here, along with our Nebula, along with our Wormhole modules, on the top, you can see a general purpose AMD EPIC based compute and a memory pool, which really opens up the capabilities on training. So this is another topology. We saw the server, we saw the rack. This is a supercomputer topology where we interconnect again the racks in a 2D fashion to really create a very large topology of mesh of cores. So you can see that the solution really scales and practically can extend to infinity. And that's one of the powerful things we have been doing here is to give the user the flexibility to really on-demand compute whatever he wants. He based on the configuration on the cloud, the user can get the right topology at the right price. So let's kind of switch gears, and I would like to touch upon how this whole scale out concept evolved. So when we were developing the solution, the idea was to really provide a solution which can scale based on the number of nodes. And the model sizes were growing, so we wanted to give a solution which can scale based on that. And also, more importantly, give the flexibility to the model designer by making sure that it's just a sea of mesh, of course, which can be configured for the ML needs. And of course, it has to be cost effective. You don't want you don't want to land up in a situation where you don't use something which is there in the hardware. So if you go back, like how it started, in the initial days, there was concept of model parallelism and data parallelism. Data parallelism was the first one which evolved, where it was done using CPUs and GPUs. But what was happening was it could get us to it could really help us to really till ResNet and BERT, but it really didn't scale as the models kept growing, particularly for like a natural language NLP type of workloads. So the issues with batch-based learning was it really ran out of batch size after a while, and then the way the solution was looking, it needed either more SRAM or it had to go to the DRAM. So really it could not scale with respect to as the workloads were emerging. And the need for more DRAM bandwidth or HBM, which is what GPU is trying to do, it was going in that direction. So what we wanted is to really make sure that the solution is not limited by these limitations. And along with that, a lot of libraries were evolving to really provide efficient scaling. You can see here a lot of these libraries started giving model parallelism and pipeline parallelism flexibility for the user, and that is when this, along with our hardware architecture, really provided the scale out opportunity. So the way we achieve this is basically, if you look at it, our microarchitecture is really has to do what is called as a place and route of our tensors. So to enable that, we have a mesh of cores, and our compiler really has a problem of making sure which tensor gets getting placed at which core, and we also break the tensor to mini tensors so that you can break down the problem and make use of the parallelism in the graph. So the actual solution was just to place and route the mini tensors, but also we noticed that when the tensor is moving from one compute to other compute, it might need other manipulations. So in general, we would like to have a hardware which can act like a network switch, which can also do minor tensor manipulations as it travels from one chip to other chip, or from one chip to the other chip on externally on an inter-die solution. So our architecture really had to have the right interconnect fabric, which can transport data across chips or within the chip. So that's the network on chip we have been developing, which really provides flexibility of packet movement in a very seamless fashion, which allows us to move the tensor from one chip to other chip or within the general chip, within our own chip. So you can see here an example where the tensor is broken down to mini tensors, but end of the day, if you look at the way it's just a packet movement, the tensor is just added, a header is added to the tensor, and it just moves across different cores, which really provides the flexibility for scaling out across chips. So this slide kind of talks about why Tenstorrent microarchitecture is really powerful. So if you look at the mesh architectures, like a sea of cores, you have FPGA-based solutions, you have coarse-grain array-based solutions, and we have the Tenstorrent microarchitecture, which is a lot different. It's a very customized hardware. So if you look at the main difference, FPGAs are lookup table-based. They were really written to model, to take an RTL and map it. It was not written for AI needs. So it tends to have its own challenges. Again, the interconnect mostly is just routes wires. And then if you want to build a system out of it, you have to manage the packets, you have to manage the DRAM traffic. And as a result of all this, it usually tends to be slow, and it's also expensive. CGRAs have more memory compared to FPGAs. But again, the interconnect fabrics and the DRAM traffic management is similar to FPGA. But if you look at the Tenstorrent microarchitecture, the compute blocks we have developed is really beyond a matrix engine. It can do manipulation of data. We have our own. So each of our 10.6 cores has a floating point unit for the arithmetic, as well as we have a sea of RISC cores trying to help with data manipulation as well as packet manipulation. And we also have our own L1 cache, part of each of our 10.6 core. And the other thing, as I was telling earlier, is the ability of our NOC to really, push the tensor more like a packet and very seamlessly across chips or across servers or racks. So this is one of our unique selling points we have. So through the internet, the NOC is really able to push the packet natively. And as a result of all these things, the solution is really fast, and it's also cheap, and it has a really great performance. So this slide it talks about the ability of our chip to, the knock inside our chip is just not doing the compute. In certain cases, you can also use our knock as a switch. So there is no need of an external switch. The packet here, if you see here, the packet comes from the tensor on the chip on the top, and it goes to the bottom. So in this case, this chip acts like a network switch. So the knock really has a capability to act like a switch. It provides a very native extension through the Ethernet. So we feel that the knock really powers our scale out solution. So in general, as I said about the capabilities of a knock, the knock really supports a very hardware supported abstraction, and it provides ability to really push the tensor or pop the tensor. You can do copying, gathering, scatter, shuffle. So in general, as a tensor moves from one chip to other chip, it really moves with less overhead. And more importantly for the programmer is just a mesh of cores with not a lot of hierarchical dependence, whether it is a server or a rack or a supercompute. There are not many overheads typically when you see multi-chip solutions, and the knock really powers it. The knock we have at Tenstorrent really powers that solution. So in summary, I would like to conclude that Tenstorrent wormhole chip really has a range of silicon improvements, which is really powering training needs. It really provides a scale-out Ethernet option to provide multi-chip, multi-server, multi-rack options, and the library features of pipeline parallelism and modern parallelism is really exploited in the hardware itself. And we have a lot of hardware supported data flow abstractions to make sure that the tensor moves with very less overhead. And last but not least, the most important thing is provides a uniform programming model for inter and intra-chip.
Thanks, Senthil Nathan, for the talk. We have a few questions in the chat. Are you able to see the chat?
Yeah, I can see it.
Okay, so George has a question. GPUs are the de facto hardware to train networks. However, there are efforts to parallelize training using CPUs with LSH. So do you consider it is worthy to research ways to accelerate the training in CPUs by means of smart algorithms, or at some point GPUs may be widely affordable and available?
This is more of a software question, but based on my knowledge, what I've seen is recently I've heard about a few papers on trying to use CPUs for machine learning. But I think the fundamental workload really requires either a DPU or a GPU type of hardware. With CPU, I feel that maybe there's some promise, but it will have its own limitations. And the industry is also going in the direction of scaling with providing the libraries to scale based on model parallelism. So in my opinion, CPUs, there will be some approaches here and there, but I think either GPUs or custom DPUs will be the right way to train ML.
Great, thank you. I think I had a question. What are your thoughts on owning the hardware versus going on the cloud? Sometimes there's not full utilization, even if we pay for the cloud services, right? So what is your opinion?
I mean, Tenstorrent, we have been promoting the cloud-based option, primarily because it provides the user an option to scale based on the need. I think for training, definitely cloud will be needed. That's what I feel. But again, we have the PCI card-based solution also and we do have some server racks apart from the cloud solution. So I think it's probably the user's choice on what he wants to do.
I think there was one more question from Ricardo, but Eric replied briefly. Ricardo said, I can't move customer data away from AWS, Azure, or Google Cloud. How does one use your hardware without breaking this sort of data protection agreements?
Probably did Eric was able to answer. I'm not sure about that. We can.
Yeah, I think he mentioned we've got a couple of options. You can own the hardware or have IaaS service that has Fabric interconnect to these services. I think, yeah, further discussion may be required for the data agreement stuff.
Okay.
Yep. So just a general question, like the design of the hardware seems to be like driven by how AI and ML field is progressing, right? But that wasn't the case before AI and ML was in full force, right? So where do you foresee the design progression for the hardware in the next 5 years or so?
Yeah, I think currently, if you look at these chips, they have a problem of reticle limit. So there is only so many number of cores you can put. So that's what limits the number of cores inside each chip, and that's why people are talking about scaling out through the Ethernet. I foresee that, like, based on what I've heard, is just a custom AI hardware may not be sufficient enough. There will be a need for custom RISC cores. So from what I've heard is like, future in future, if you want to build the right hardware, it'll be a mix of a custom AI hardware plus a CPU, a high performance CPU, and a software which manages all this. So that's the direction. It's what I heard is lot of ML workloads also in need of more general purpose freestyle coding also is there. So in the last 10 years, the focus was on matrix multiplication and linear algebra to support linear algebra. But I think the way things are going, you will need some kind of CPU compute also inside inside the custom cores. So that's the direction I think industry is heading.
Right, thank you. And I think Kelvin had the same thing too. Do you foresee AI machine learning to design these AI chips? So Eric did answer. There's potential to leverage AI in chip design as well. Yeah, that's interesting.
Yeah, I saw a paper from Google. I think currently, if you dive into how the CPU design is done, we typically build one core and we stamp it many number of times. So what Google is talking about is inside the chip where you place your design. I think they are trying to use some ML approach. I'm from physical design, so we still use a lot of these tools and a lot of work is done manually. So because Google is so good in software, they're trying to solve that problem using ML. And the current place and route tools from Synopsys, Cadence, all these EDA companies also, they are coming up with some new ways to do chip design based on ML, but it is not prime time yet. They're just talking about it. I think a lot of work is still done very manually, and there is a reason for it, because when you are as a chip designer, if you're trying to optimize for performance, power, and area, you still have to do a lot of experiments and figure out the right thing, which they're trying to solve by software. So yeah, there has been some news from EDA companies trying to solve that problem using ML. So yeah, that's another interesting thing which is happening on the design. You design a hardware to solve a problem that itself gives you another solution. So
yeah, it's definitely in a very beginning stages. Yeah. think we're running out of time. On behalf of TMLS team and everyone, I'd like to thank you, Senthil Nathan, once again. I encourage attendees to visit our partner booths to enter in exciting giveaways.